Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process by quoting a statement by Sally Ride, that is, space shuttle is a better and safer rocket than it was before the Challenger accident. All of you might be aware about the accident occurred during the Challenger's flight, and around 7 people died, out of which 5 of them are astronauts. So, if you look at it, is sometimes accident or any other mishaps help us to think and also rejuvenate our program, and such that you can get better result from the safety point of view and also effectiveness point of view. And let us recall what we learned in the last lecture. In the last lecture, we basically discussed about the characteristics velocity. The characteristic velocity was basically a function of the temperature, chamber temperature and gamma, and always we need to have a higher characteristic velocity to have a higher ISP. You can recall that ISP is equal to Cf C star divided by G, and later on we also discuss about took a problem and then look at it, and higher characteristics velocity always one wants to have a higher characteristics velocity, but unfortunately we cannot take higher values because of fact that temperature, higher temperature cannot be achieved. Today we will be discussing about how this actual rocket engine is different than the ideal one what we have discussed till now, and let us look at what are the losses in actual rocket engines. We know that in case of a convergent divergence nozzle, then the flow divergence is likely to occur. As a result, losses in the axial momentum is inevitable, and that can lead to the lower specific impulse. And of course, to overcome these problems, people have designed another nozzle which is known as bell shaped nozzle or the contour nozzle to minimize the losses due to the flow divergence. Little bit later on, we will be also deriving how this flow divergence parameter can lead to losses, and we will derive an expression for flow divergence correction factor. And generally, the velocity in the combustion chamber is being considered to be almost 0 in our analysis, particularly under ideal condition. However, the velocity will always be some tangible value, because of fact that there will be acceleration of the flow due to the heat addition, and as a result there will be certain Mach number of course subsonic values around 0.2 is being almost there, and as a result there will be pressure losses due to the heat release and also leading to the lower thrust. So, that is also one of the reason why the actual rocket nozzle performance is lower as compared to ideal one. And beside this, sometimes the combustion need not to be completed in the thrust chamber. It can be extended in the particularly convergent portion of the nozzle, and as a result the flow properties will be changing because the equilibrium has not reached, and so also the spaces which will be goes on changing, and so also the temperature. As a result, the characteristics of the ideal nozzle will be altered, and that also affect the performance of ideal nozzle as compared to the actual one. In other words, the performance of actual nozzle will be different than the ideal nozzle. And what we have assumed that uniform gas composition in the nozzle, but which is not true because of temperature. It will be changing, and also there will be some combustion might be taking place, as just now we discussed, and as a result it can cause losses due to inadequate mixing and incomplete combustions. And beside this, the pressure drop in the combustion chamber due to heat release, flow separation, mixings do occur, and that has to be taken care. Otherwise we cannot, and we assume that there is no pressure losses in the combustion chamber, the thrust chamber, in our analysis for ideal rocket nozzle. And we have assumed adiabatic flow, or the isentropic flow rather. The heat losses to the casing and nozzle walls is inevitable, even though you can have a insulation, but still heat losses will be there. The boundary layer also will be there, will be on the wall of the rocket nozzles, but that we have assumed there is no boundary layer, it is inviscid fluid. And in real rocket engines, the boundary layer will be leading to the decreasing the effective exhaust velocity by around 0.5 to 1.5%. That can result in a lower thrust level. And beside this, we have assumed the gases should be there in the rocket nozzles, but however there might be solid particles, droplets, which will be flowing along with the gases in the nozzle, and that can cause losses in the actual rocket nozzle. So always we assume that optimum nozzle expansions, but actually in real situation, as the rocket nozzle will be moving through the altitude atmosphere, then naturally there will be non-optimum nozzle expansion will be occurring, and that can cause losses in exhaust velocity, leading to lowering of specific impulse. As I told that maybe particular nozzle will be designed at a particular altitude, however one has to travel through the certain altitudes. So the nozzle is subjected to over expansion, under expansion, and during its flight which will be incurring losses as high as 15% as compared to the ideal nozzle. Hence advanced nozzles are being developed to compensate its performance for altitude. So which we will be discussing little bit probably in the today's lecture. So these are the losses which will be occurring in the actual rocket engine. So therefore the performance of actual rocket nozzle will be lower as compared to the ideal one. And beside this, the unsteady combustion pressure fluctuation can lower the nozzle performance, which is may likely occur due to the different various regions. Let us now look at the effect of divergence angle on the thrust produced by the engine due to the expansion of the high temperature and pressure gas in the nozzle, conversion nozzle. So for that, let us look at the schematic diagram of a conical CD nozzle, and this is your CD nozzle, and it is having a conversion portion and a throat area and divergent portion, and this is your axis, and you can say this is an x direction and this is your r direction, and this is having the RE. RE is basically the exit radius of the nozzle, and it is having a throat area. So I can say this is RT, and this makes an angle alpha with respect to axis. So if I that this is basically origin, you can say this making an angle alpha, and if I consider the flow to be along with this direction in along with the wall VE, if you look at this point at the exit, the VE will be along with the axis, that means VE is equal to the Vx, and it makes, this will be making an angle alpha. So, if you look at, this is the, let us say, velocity, this makes an alpha, and this alpha is basically semi divergence angle of nozzle. And if you look at, if I will take this component along the axial direction, it will be basically VE cos alpha. And if you look at the axis, this angle, that means angle of the flow from the exit of the nozzle is 0, but as it moves along with the radial direction towards the wall, you will find that this angle alpha is changing. That means it is the flow divergence angle is changing from 0 at the axis to the maximum near the wall, alpha is equal to 0. In this case, we are not considering the boundary layer effect, we are considering only the flow divergence. Keep in mind that there will be boundary layer on the wall of the nozzle, this is wall. So, therefore, we can say that average angle at which the overall stream leaves the nozzle, the average angle at which overall, at which leaves the nozzle will be equal to, basically if I take average, it will be alpha by 2 with respect to axis. So, then you can say the thrust produced by the actual thrust produced by the thrust along the x direction would be, that is Fx actual is the thrust produced along axis, and this is actual thrust produced along with the axis, will become basically, that is Fx actual, let us say mass flow rate of the propellant which is passing through this nozzle, into this is will be having this direction, total mass will be passing through, and this will be m dot v into cos alpha 2, alpha divided by 2, and the velocity, average velocity, if you look at, this is alpha by 2. So, therefore, this will be basically Vx is equal to Ve cos alpha by 2. So, then it become Ve cos alpha by 2. So, therefore, I can write down this is equal to m dot Ve cos square alpha by 2. We know from trigonometry that cos square alpha by 2 minus sin square alpha by 2 is equal to 2 cos square alpha by 2 minus 1 is equal to cos alpha. So, therefore, I can write down cos square alpha by 2 is equal to 1 plus cos alpha divided by 2. So, let us define a divergence factor or divergence coefficient, correction coefficient, or lambda d, that is basically actual in the actual thrust along the axial direction divided by ideal along the x direction. So, that you can see that it is nothing but your m dot v cos square alpha by 2 divided by actual one along the direction will be m dot into V e. So, these will cancel it out, and cos square alpha by 2 is basically 1 plus cos alpha divided by 2. That means this divergence correction factor is basically what we have derived 1 plus cos alpha by 2 when alpha is equal to 0, which is not possible, but however let us hypothesize. That means the actual actual thrust produced along the axial direction is same as that of the ideal one. And keep in mind that the losses due to this divergence, loss of thrust due to the divergent flow in a convergent conical nozzle can be expressed as F loss in the thrust is equal to 1 minus lambda into 100%. If you take this various angle and see that what are the divergence factor we are having, what are the losses we are having, let us vary these parameters and see that at the 0, as I told, divergence correction factor is 1 and the loss of thrust will be 0. Of course, it is very difficult to achieve in a CD nozzle, but you can take a 5 degree divergence angle, that is divergence correction from 0.998 and loss factor is 0.2%, quite low. And if you goes on increasing, you see that the divergence correction factor is increasing, so also the losses. And you can see that from 5 degree to the 20 degree, when you go, it is something around 3 divided by 0.2, it is basically 15 times. You can see that it is being increased the losses. And of course, when you go for 25 degree, the losses is very higher, that is 5% losses. And always if you want to go for a smaller divergence angle, naturally the length of the nozzle will be very, very high. And you can see, let us derive the length of the divergent portion of nozzle, and we can see that this is basically, this is the length L d, and this is your angle alpha. And if you look at this portion, that is nothing but R e minus R t, and you can find that the L d is basically length of divergent duct is equal to R e minus R t into cot alpha. So, you can see that means this alpha increases, then you find that the length of the divergent portion of the CD nozzle decreases, and when it decreases, however, for smaller one it becomes very higher length, and higher length means the weight will be higher. You can see that this will be basically when the angle increases from 5 to 15, and then the length will be increasing something 3 times. So, as a result, generally the divergence angle is restricted to 15 degree, because losses are not much, and then also the length won't be very much. So, that is the reason why the divergence angle is restricted to 15 degree. Because of this limitation of the convergent divergent nozzle, there are various types of nozzle as being designed and developed. As I told that convergent divergent nozzle, generally the 15 degree is being used as the angle because of fact just now I discussed. And another rocket nozzle is known as the bell shaped nozzle. In this case, it is such that the angle, the divergence angle is changed from the throat to the exit in such that the divergence effect will not be there. So, as a result, the divergence correction factor will be very small values. You can see that this theta n is much higher values of theta near the throat nozzle is being used. It is something around maybe 20 to 50 degree is being used, whereas in the convergent divergent nozzle it is generally restricted to 15 degree, and this angle is something 2 to 3 degree is being varied. And keep in mind that one can go for a little lower one, but and also it is higher, that this parabola plays a very important role, such that no flow separation will be taking place, particularly when it is operated under the non-optimal condition. And this bell shaped CD nozzle was basically designed by Dr. Rao in the for the first time, and he has of course mentioned various radius and for different rocket nozzle size and shape. Keep in mind that this is being very much used. However, in order to overcome the problems of the flow separation in the rocket nozzle, so this is being used. This rocket nozzle is various other design has been used, because the convergent divergent nozzle has to go through various altitude where the atmospheric pressure will be changing. For that people have designed a extendable CD nozzle, in which case like there will be this extendable segment will be actuated at a high altitude, whereas for the low altitude, this is the low altitude, the lower area ratio nozzle is being used, and so that it will be adapted properly, losses will be minimized. But however, in case of a high altitude operation, that is AE, this extendable portion is being used. Problem with that it has to be actuated properly, otherwise there will be a thing, and there might be some losses due to this deployment of this extendable segment of the nozzle. And also thrust requirement, because will be very high, because you will have to use some force to extend this segment. This will be having parasite effect on the performance of the rocket nozzle. And in order to overcome that, people have gone for something having two bells nozzle. This is one bell, the first bell, and this is the second bell with a bump. In such that when it is operated at the low altitude, this will be flow will be separated. As a result, the flow velocity which will be taking place, it will be going that way at the low altitudes. But however, when the it is operated at the high altitude, let us say with the A2 high altitude, then this flow this bump will not, and the flow will be taking place over here, and so that it will be operated as if it could see the higher area ratio, and then it will be adjusted so that the losses will be not there. And beside this, there are another two nozzles which are being used very much. One is Aerospace nozzle and other is deflection expansion nozzles, and which are exotic nozzle which are not being used, but it is a lot of experiments are going on to find out its performance, and people are having opinion that it can operate well along with the alt altitude. In other words, it can be adjusted well along with all the altitude. Thank you very much.